One. Okay. So welcome to today's Colloquium talk. And in fact, today's speaker is the organizer of this Colloquium series, Nishant Chandgotia. I think Nishant doesn't need any introduction because he's one of our own, and you all know him. So he's going to talk about some questions about tiling. So floor is all yours, Nishant.
Thank you very much, Ujjwal, for the introduction. Thank you to the audience for coming for my talk and listening to me. So today I'll be talking about some questions related to tilings. So most of the talk will be somewhat introductory, and I don't plan to delve into the mathematics too much. At the same time, I want everyone to be with me. I'll be hopefully asking some elementary questions, and I hope for some audience participation. I'd be especially pleased if people would switch on their cameras so that I can actually see if somebody's following, how are things going. It would feedback would be much appreciated. All right, so let me talk about the prerequisites for this talk. So what you can see are jigsaw puzzle pieces, and when I was very young, my mother would buy lots and lots of these for me, and these are very simple things, right? Two-dimensional pieces, and there are some rules in which you can put them together. Like if you have something sticking out like this, then it better fit in something like this, and then you put them together, a nice design comes out. And it would give me immense pleasure and make sure that I was away from troubles with all the way through. And what my mother did not know back then is that she was training me for the mathematics I was about to do later in life. In fact, most of my research career is somehow related to taking these finite pieces, putting them together in particular ways, and studying them as much as I can. So, as I said, I will not be talking a lot about my own personal research, and it will be sort of introductory. So, let me start with the basic problem. So, suppose we are given infinite copies of some square tiles, and all these square tiles, there are some colors given to you. So, for instance, these two tiles, you have green given here, and you have green over here as well. And similarly, this black. So what is the function of these colors? So these are some rules on how these can be put together. Just imagine that you actually had a jigsaw piece here, and this would be sticking out this way, and this would be anyhow. So there's some rules on about how these things can be put together. And what do we have to do? We put them together and we tile the plane. Okay. So what I've done is I've taken some copies of these, and I've followed the rule that I can only put them together if the edges match. So as you can zoom into this, you see that these colors match, these colors match. I have not cheated anywhere. It works perfectly fine. Okay. So this is the game. You're given tiles, you're given colors on edges, you're given rules on how these tiles can be put together. And now I want to tile the plane. Of course, just to emphasize the point a little further, if the colors don't match, for example, this is orange, this is blue, I cannot put them together. This is green, this is black, I cannot put them together. So this is not allowed. Now, the question that we want to ask is the following. I will give you a finite set of tiles with color specified. I won't let you rotate the tiles or anything. I'll give it to you in a particular orientation, with a particular orientation. And the question I will ask you is, can you cover the entire Z2 lattice with these tiles? Okay. So here's an example that we considered before. And of course, you can tile this periodically because, you can see that you have these pieces and you can just keep on repeating what you see over here everywhere and just repeating these pieces. Okay, and that's because your blue will fit with this blue over here, this orange will fit with this orange, and there's really not much to play with. In fact, one can prove that if you have only two such tiles, it will always be periodic. And I think the record for this is 11, I believe, which was proved by a French mathematician after tons and tons of computer search. So if you have less than 11 tiles, then all the tilings will be periodic. Sorry, not all the tiles. Sorry, what did I say? Then there is a way to periodically tile the plane. Now, what about these tiles? So it's towards the audience. Do you think I can tile the plane with these 4 tiles or I cannot? Just to make sure that everyone is following, or at least one person is following, whoever answers.
There is a dark green there, or is it supposed to be something?
There is one color which looks.
I don't know the answer, but I have a question. So, like, are there 3?
Subhajit, we could not hear your question. Can you repeat it?
Sorry, I clearly got disconnected. I feared this would happen. Normally, I have my own personal internet for these kind of for the talks, but somehow my computer has stopped accepting Wi-Fi, and we are trying to fix it. I'm extremely sorry for this. I should have just used my laptop. So what I had last asked, and I don't know if you. Was everyone with me till here? Okay, so now the question was whether these 4 tiles can tile the plane.
Yeah, here I have a question, sir. So
Yes.
Are there 3 shades of green or 2 shades of green?
There are 2 shades of green, this shade, and then, I see what I have done. And yeah, there are 3 shades of green, but it doesn't really matter.
Okay.
But just because we lost a minute, let me just tell you, you cannot tile the plane with these 4 things, because clearly if I was to put this, then I would be forced to put this tile at its bottom. Then to the right, I would be forced to put this tile. And then I would be forced to put this tile, but these 2 colors don't match. So there's no tiling possible because when you have these. So if somebody gives, so here's the general question that I would like to ask you. So I give you a bunch of tiles and I ask you, can you use them to tile the plane? What would you try to do? Anyone?
Create larger and larger rectangles which are tiled by that.
Absolutely. So this is the only thing you can really do, right? You just start trying to put them together and in whatever way you can. And if at some point we see that we cannot tile any more longer, like there's just no extension to it, then we know that no such tiling exists. On the other hand, if I get something periodic, then I'm in very good shape, right? So if you look very carefully, all the colors up here match up with the colors at the bottom. All the colors right on the left match up with the colors over here. So this just means I can take these shapes and I can put them together and I'll get a tiling of the entire plane. So somehow these periodic tilings play an extremely important role. it gives me the answer immediately that I can tile the plane with these given tiles. So is there a problem with the strategy, right? So what is our strategy? As Abhishek had suggested, we take these tiles, we try to put them together, and if at some point either we fail, like we can't extend this tiling anymore, then we are done. Or if we make this periodic, then we know that we can just put them like sort of in a periodic fashion, then again I'm done. What is the problem with this strategy?
Maybe you don't get a periodic.
Sorry, Kaushik?
No, it may happen that you may not get a periodic.
Exactly. That I might just keep on doing this till infinity. And as much as I love these puzzles, I don't want to spend my entire life just putting tiles together, right? I would like to, end the process somewhere. And this is precisely how Wang asked. Suppose there is a way to tile the plane, the entire plane. Is there necessarily a way to tile the plane periodically? Wang was interested in an automated theorem proving, he comes from logic, and this is where the question arose from. And if the answer is yes, then we have an algorithm to decide whether a given set of tiles can tile the plane, right? The algorithm will be that you just keep on trying to tile, and eventually you'll either be periodic or you will fail to tile. So as all good question makers do, he gave this question to his PhD student. And the answer is no. There is no algorithm which can decide whether or not a given set of tiles can tile the plane. So you can write down an algorithm. If I give you a specific set of tiles, maybe you'll be able to give me a yes or no answer. But in generality, for every tile set, it does not exist a common algorithm. In other words, this problem is undecidable. So here's a question: how does one go about proving this? Let me give you a flavor of how one goes about proving something like this. So the germ of this idea, like I heard it while listening to a talk by Avi Whitbison, is something called, he put it as a refutation of Hilbert's dream. So two important questions which Hilbert raised is whether, whatever is true is provable, and whether if something is provable, is it computable? So we are all sort of vaguely familiar with what these words are, and I'm not going to put them, sort of define them in any way. We'll keep it at this vague level. And so we are all familiar with Gödel's incompleteness theorem, which tells us that no reasonable axiomatic system, there will be definitely statements which will neither be true or false. And this sort of negates the possibility of the first equality. The second equality, it comes from Alan Turing's thesis. If you have ever heard of Turing machines, which are formalizations or a formal way of looking at whatever we can compute or how our computers work, showed that there are provable things which cannot be computed. If you take a machine, then it will halt at some time. If I give you a set of tilings, it either tiles the plane or it doesn't. Like one of these two statements is true. So Turing's thesis showed that, there are provable things which are not computed. And specifically, there's no algorithm which can decide whether a given algorithm will halt or not. This is called the halting problem. It's a very well-known problem. And this was sort of like I'm putting a huge body of work in a few lines. So the main thing that I want you to remember here is that there are things in nature which we know which are undecidable. And in fact, very particular things. For example, I cannot decide, I can't have a method which will look at a particular algorithm and tell whether or not it will stop after finite time. And so this is what I was talking about. It's either true or false, one of the things there can be, but there can't be any general method to solve this question. So what did Berger do? Berger produced a set of tiles which can only tile aperiodically. Like this is sort of what you have to do. And then he somehow superimposed these symbols of computation, these computation machines, following the formalism of Turing. So it was a very ingenious proof that he did. Since there's no algorithm, and what would happen is that these set of tiles, which can only tile periodically, and then there has this superimposition of the symbols of computation, the computation will keep on going on, right? But to ensure that I can tile the entire plane with these tiles, I would have to have that the computation should end in infinity, should not end ever, should not end in finite time. Now, since there's no algorithm to decide whether or not a computation will end or not, there's no algorithm to decide whether a set of tiles can tile the plane. And these are the tiles which he used. These are arrows. These would be, these would form, like, you would have to attach the arrows in this way. And when you put the arrows together, the only kind of configurations that you would get would be these hierarchical structures, which look like this. So you have these boxes in still bigger boxes, in still bigger boxes, and so on and so forth. And the space between these boxes would be where these symbols of computations would lie. So all computations would begin at the lower line, they would continue up until the top. And if you want to ensure that I can tile, say, this box, I would need to ensure that this computation of this Turing machine, this program, can run all the way till the top. And very, very vaguely, this is the crux of this idea, how he proved that you can't decide the tiling problem. So there's a simplification done by Robinson. This is a good time to ask, is the idea clear? At least do you understand that periodic points are interesting and important? That's probably
no, I don't.
Yes,
I
there's
don't.
a question.
Can you just repeat from the previous slide, because I think I lost you. The
Ah,
previous slide when you showed the tiles with the arrows.
yeah. So
now the arrows should so I should be able to tile only if the arrow goes to the head of the arrow goes to the bottom, the toe of the arrow.
Right. So here rotation is allowed. I can rotate these tiles as well.
I see. Okay, so rotations are allowed. Okay, all right. And then in this configuration, so how is this related to the next slide? So
Right.
what do I get? What is inside the smaller boxes and what is inside the bigger boxes?
So it's actually a lot more complicated than what I gave you. There are in fact 32 tiles, and I didn't want to give you all of them.
Okay, fine. But there are more tiles, I understand. But how do I get to the red
Right.
box?
So the thing is, if you follow these bigger arrows, these are called double crosses, then you get shapes like these. So
what is this shape? What is a small box? So a small box is tiles. I
Yes.
see. And these basically the arrows depict the boundary of the square, is it?
Exactly.
I see. Thank you. Okay, that explains now. Okay, thank you.
Thank you for the question. Please interrupt me if things are not clear. Right. And so,
sorry, what is the problem then? If I have these boxes inside boxes and so on?
Okay, so the problem is now I will superimpose on these tiles these symbols of computation, and these symbols of computation will start at the bottom row, and they have to keep on going up until this place. So there have to be these many steps of computation starting at the bottom row. Now, I can create a set of tiles for any program that you write in the world. I can create a set of tiles for that program. And since I can't decide whether or not a program ends, I can't decide whether these superimposed tiles will be able to tile bigger and bigger boxes or not. And that's the problem.
Okay, I understand. So there is some sort of a matching between the Turing symbol and the styling problem.
Right, exactly. Okay. Not a matching, I would say, but some sort of embedding. Like for each program that you write, I'll give you a set of symbols. And if you really want details, then next semester I'll be teaching this. Hopefully.
That's a good advertisement.
So this is very fascinating. But this was 1966. Robinson's examples was 1972. 1974, Roger Penrose came along and gave a set of tiles which cannot. These are no longer squares. He's looking at the plane, and it gives rise to these aperiodic tilings of the plane. And why did he do this? He wrote a paper on this. One thing that I would like you to point out is that it has some sort of symmetry, right? If you look at this shape over here, why did I put my pen inside? Sorry. Yeah. Then there's some sort of 5-fold symmetry over here. This is very important. Just keep this in mind, and we'll come back to it. And what was his motivation? He had a friend in a hospital, and he wanted to design something which looks nice. That was essentially it. But what it did is, he was already very famous, and he does something, and this kicked off a huge body of work with many such tile sets being created, everybody creating their own tiles, which tiles are playing aperiodically. In 1981, Steinhardt, Nelson, and Ronketti predicted that there must exist such a crystal which has such structure. This prediction went against the crystallographic restriction theorem, which said that crystals should only have 3, 4, or 6-fold rotational symmetry. And this came from the fact that all crystals must be periodic. This was the assumption. This was what people thought was true. And this goes back a very long way, hundreds and hundreds of years. However, in 1982, Daniel Shakeman, with no knowledge of these theoretical, he was a chemist, he didn't know about all these theoretical developments, noticed that the diffraction pattern on certain alloys had 10-fold symmetry. And this fascinated him because this was completely against whatever was known back then. And this broke the misconception that, orderly arrangement of atoms necessarily has to be periodic. There was a big, big revolution in the field of crystallography, in material science, a completely different perspective. However, he was not taken very nicely. So this is a 2 times Nobel laureate, Lynn Spalding, who said that there are no quasi-crystals, but there are quasi-scientists. So Shakeman lost his job, lost his, he was sort of completely removed from the scientific community in some sense. But people gradually checked. There were these theoretical backings as well, and he eventually won the Nobel Prize in chemistry. So it's kind of interesting. I'm not sure if all these, unless all these theoretical developments had taken place, there would be much backing for Shakeman, even though some very huge people thought that, very well-known people thought that he was completely nuts. And there's been recently a certain alloy seen under an electronic microscope showed structure very similar to Penrose tilings. And there he was just drawing something for someone to just look at. So, these curious puzzles and doodles can also lead to something interesting. Okay, so this is all modern science. I've spoken about Nobel Prizes and God knows what not, like and big landmark papers in the field of tilings. It's all like last 50 years. But it turns out if one picks up Kepler's book, and I did, one finds tilings very, very similar to, what that was, the kind of tilings that we are seeing in these papers. And this was 1619, and Kepler was interested in crystallography. He was one of the founding fathers of crystallography. So it's clear that, he was thinking about these objects. It's not a coincidence that he designed what he designed. And this goes back to 1453. So, and there, if you look at art, then you'll probably see many more instances where people actually try to construct something like this. So, this is a quote which I read from a book on thermodynamic formalism by Noel, which is where I learned most of my thermodynamic statistical physics from. There's a lot of truth in this, at least in mathematics, where similar ideas keep on coming back in one form or the other. And we are always moving ahead, but somehow we are reinventing at the same time. Anyhow, so I'm about 30 minutes done. So 30 minutes up. So before I move on to the next slide, where I'll start going a little into what I am interested in and what I have done, are there any questions? All right. So let me tell you what are the objectives I would like to achieve in the next 20 minutes or so. So there are 3 objectives. So the first objective that I would like to know is, suppose we can tile the plane by a given set of tiles. The question that I want to ask is, can we approximately count how many of them are there? By this does not mean that I want you to give me an answer or a little number. I want to give an approximation, give me some sort of ideas how many of them must be there. The second question which I would like to address is, okay, so these tilings are nice, but what can the tilings say about the world? What kind of processes can they model? Now, of course, modeling means different things for different people. I mean a very specific kind of modeling, which is modeling ergodic processes, modeling ZD actions on Borel spaces. And I'll talk about all of this as time comes. So somehow you can start looking at the space of tilings as a compact space on their own. So this would give you a compact space, and translations leave this space invariant. And now you can ask whether things can be embedded in them, whether other actions can be embedded in this. And the third question is, and which is for me currently the most exciting part, and which I'll talk the least about, is what does a random tiling actually look like? So somebody gives you, a bunch of tiles, and you do it as randomly as you want. What will the random tiling actually look like? So these are 3 questions, 3 objectives, which we would like to, get to in the next 20 minutes. So let's try to look at the first question. So suppose we can tile the plane with a given set of tiles. Can we approximately count how many of them are there? So people who attended my class in the morning might get bored, but let's formalize this and talk about this. So what do we have? Okay, so now forget about the tiles, forget about the colors. Let's look at it abstractly. What do we have? We have a finite set And we have some rules R which tell us how symbols can be placed next to each other. That's all right. Each tile, give it a name, and now you tell whether it can be put left to it, can we put it on right, can we put it on the bottom, can we put it above in ZD lattice, so whatever dimensions you want to. The space of configurations following these rules are what are called shifts of finite type. I'm not using the general definition. There's a more general definition, which we don't have to get into for this talk, for the purpose of this talk. So just to have some examples in mind, just take a bunch of boxes, rectangular boxes. The only restriction I would put here is, so that the space be a little interesting, is that the greatest common divisor of the sides is 1. So here, if I look at the horizontal sides, then there are 2 and 3, and the vertical sides are 3, 2, 1, and 2. In all cases, the GCD is 1. Okay. And now what I want to look at are tilings by these rectangular shapes. And this is a shift of finite type. One can look at shifts of finite type in this way. An extremely, extremely important subcase of this is that of domino tilings, where all the sides have length 1 except one edge which has length 2. Okay, so dominoes are just these 2 by 1 by 1 by 1 objects. So here's a tiling by these boxes that I had before. And here is tiling by dominoes. So this is 2 by 1. This is 1 by 2, and so on and so forth. Okay. Does everyone understand what a domino tiling is? Otherwise, you won't follow much of the rest of the talk.
Could you please repeat what is domino tiling?
So domino tilings is just tilings by boxes of such that all the sides have 1, sides have size 1, except one side which has length 2. Sorry for my terrible handwriting. So this has side length 1, and this has side length 2. This is side length 2, this is side length 1. So these are all tilings by 2 by 1, 1 by 2 boxes. Okay. Is it clear?
Yeah.
Okay. Great. So this was the general object that we had defined, finite alphabet, rules and how it can be put together. We know by now that there's no algorithm which will tell me whether the space is empty or not, whether there's something which follows all these rules and tiles the entire plane. Covers the entire plane. Yet we can define this quantity SNR, which is the number of different patterns on an n box which follow the rule. Okay, and this is something which I can really compute, right? I take a n by n box and I look at all the ways in which I can fill the space inside, all the ways. And there are how many symbols are there? There are about cardinality a to the power n squared symbols, configurations that I have to check. And I check whether which of these follow the rules and which of them don't. Okay, so this number can be computed. It might take you a ridiculous amount of time to do it, exponential in n square, but you can actually do it. The entropy of the shift space associated with these rules R is given by the growth rate of this number. So this is nothing but the growth rate. So now we are not just interested in, oh, does it tile the plane or not? I actually want to know how many different tilings there are. How many different ways I can arrange the alphabet A so that I can fill this box of size n by n. If it goes to 0 at some point, then it will just become minus infinity. Otherwise, it will be some non-negative number. One can show that the limit exists by subadditive arguments. Okay, so this is an important definition. I'll give you a minute to take this in. It's just capturing how many different ways, if you go back to the tilings, how many different ways can the tiles be arranged in a box? That's about it. All right. Yes, there was a question. Kaushik?
No, I mean, this computing SN, this asymptotic might be very hard. No, I mean, depending on, so
Sure.
I don't understand. Okay, I can understand this quantity is defined, but I mean, this is for most patterns, it's going to be an exceedingly hard problem to get even asymptotics.
Absolutely. Thank you, Kaushik. This is an excellent point. And it more or less sort of motivates a lot of my research. And indeed, so in 1961, Castellan computed the entropy of domino tilings in 2 dimensions. So this was later formed. So he didn't exactly do that. He computed tilings of a box, but one can actually use it and with some tricks and show that it gives you the entropy of the entire object. And it was this nice, beautiful formula which comes about because of various structures called Pfaffians, which are associated with them. An important thing that I would like you to note here is T is equal to 2. But as Kaushik was saying, that it is very rare in this study to have these precise computations. In fact, even having some sort of approximation. And it's a very hard question. And there's a very important theoretical reason for that. So the entropy is given by this formula, this asymptotic growth rate. And it turns out that if I just finish at some point n, then I get an upper bound for this limit. This just follows from subadditivity. So every time I make this computation, I'm getting an upper bound. So even though we cannot say whether the shift space is empty or not, we can approximate entropy from above. So there you are. I have a algorithm. I can't compute the entropy, but I've given you an algorithm to compute the entropy, right? I cannot compute. Sorry, I said something wrong, but anyhow, yeah, there was a question.
Yeah, so is the subadditivity easy to see? I don't see it.
Right. So the way you look at it is the following. You take this box. Now I'm going to do a very simple case of this. Now, if something follows all the rules on this big box, then it must follow all the rules in the smaller boxes as well. So the number of ways you can fill this up will be less than the number of ways you can fill this one, plus the number of ways you can, multiplied by the number of ways you can fill this. So what I'm saying is that S, and now I'm changing the notation a little bit, hopefully it will be clear, will be less than equal to S of A of R.
Yeah, I see it now. Thank you.
SP of R. And that's really the main idea.
I understand. Thank you.
Other questions? All right. So, okay, so I gave you some algorithm to approximate this from above, right? It might be a very bad algorithm, but anyhow. So a number is called right recursively enumerable if there's an algorithm which can approximate it from above. Okay, so there's a definition. You can ask, oh, if I can approximate it from above, Can't I just approximate it from below as well? The answer is no, they are different. And it turns out, and it's a landmark paper of Hoffman and Meyerovitch from 2010, where they prove that a number is an entropy of some such object if and only if it is non-negative and it is right recursively enumerable. So, somehow the only way you can compute this entropy is you can approximate it from above. This is the only general game in town. You can't do anything else. And this is kind of mind-boggling. So, we can approximate the entropy of these objects of finite type from above, but we cannot necessarily do it from below. But this is a general thing, right? For all possible ways of matching rules, all ways of which you can, rules that you put on them. In nice cases, approximation from below should also be possible, right? Because, for example, square root 2 is a right recursively enumerable number. You can approximate it from above, so it is an entropy of something. So there are cases in which you can approximate it from below as well. For instance, this follows if you have enough periodic points. How do periodic points play a role? Very simple. So what was a periodic point again? It was those where the top matches the bottom, the left matches the right. And now we look at all periodic points of period n. How does it help us? Well, if I look at the tiling of a plane, then in all of these boxes, I can put whichever element of this, provided the edges match. So I'm not going to go into the specific computations because I'm running out of time, but I can once I know that an element has matching left and right and up and down edges, I can take any element from here and I can put it in these boxes randomly. And these are giving me exponentially in many ways of, covering the plane. So this would show that the entropy has a lower bound in terms of the periodic points. And if by coincidence or by some magic, I know that it's in fact equal, then I have an approximation from below as well. So if I have a lot of periodic points, then I'm done. Now, even the simplest cases, this is extremely hard to prove or disprove. Well, disproving it is extremely, extremely hard. So one question which I pose to the audience is, for instance, look at these simple tilings by rectangles. Is the entropy of this space computable? Are there a lot of periodic points? This is wide open. Nobody has a clue. In domino tilings, things can be handled quite well. And you tile, and you get something which matches. So the entropy of domino tilings is computable in all dimensions. It is periodic points are dense. They are very nicely behaved. In d equal to 2, this followed from exact computations by Castellan. He actually found a formula for these things. In higher dimensions, you have to be a little more, you have to find softer ways of approaching this problem. So here's a simpler question than that. Suppose I give you, what did I do here? I started with something which was not a perfect tiling, and I extended it to a perfect tiling of a rectangle, of a big enough box. Can a partial tiling by rectangles be completed to a larger tiling of a box? This is a very simple combinatorial question. For d equal to 2, this is known in the case of 2 tiles. This is due to Manfred-Einstein. Okay. So this was about the first objective. Now let's talk about the
So
second
Nishant,
one.
is that like some kind of Hall's marriage kind of thing, or because
Uh,
it sounds somewhat like Latin squares, filling
Right,
up
so-
that kind of stuff, right? But
So
it's
it
probably
would
much
be,
harder. Yeah.
so it would be Hall's marriage if I was looking at domino tilings. There I would be asking the question whether I'm given this box. I don't know whether tiling of this area exists. Does it follow Hall's marriage theorem? This is what we would be asking. But once you go to a general setting where you're looking at rectangles in general, then I don't know what I can use. If there's any general theorem, anything in this direction would be very interesting for sure. Another comment about Hall's marriage, even in 2 dimensions, applying Hall's marriage directly here is not easy. In 3 dimensions and all, it becomes harder, of course. So in fact, a lot of my questions often turned out, oh, if I knew how to apply Hall's marriage, I would be done right now. And then I spend another 30 pages in trying to figure out why I can apply it. But I think we will not get to that part in today's talk. Okay, so other questions? Did I answer your question, Kaushik?
Yeah, I got it that it's harder in most cases. So just it seemed, kind of close to Hall's marriage type question. That's why I asked.
Absolutely, absolutely. It is close to Hall's marriage in that sense. Yes. In fact, if you want to find domino tilings, then that's sort of the only game in town. That's what you look at first. And it's an excellent starting point, in fact. But yes, in general rectangles, I would love to find general theorems which would enable me to do this. So so I have about 2 to 3 minutes left. So I think I'll have to skip over this, which was sort of the bulk of my research. And I'll go to the last part where
So
I just
Nishant, your screen is a bit, can you like minimize it or something? Because the screen is a bit, at least for me, it seems it's not oriented properly. I can only see half of it.
Oh, that is strange.
Works
is
fine
it-
for me, looks fine to me.
Okay. Already, yeah, now it's okay. Yeah, thanks.
Sure. Right. So I'll have to skip over this part, and I'll end with, I'll go to this question where I just wanted to show some pictures. So the question here is essentially the following. You take a certain region and you know that it can be tiled by dominoes. Now the question we want to ask is, what does a random domino tiling actually look like? And Castellan already saw that how the kind of regions he was looking at were like this, like a box. So he computed things for the box. And he noticed that if you change this even slightly, for example, a very nice example is when you take the notched cube, then suddenly there's no tiling of this by dominoes. It's a very nice exercise. I can leave with it. So there is definitely a huge influence of the boundary. And an understanding of this, the general question here is that suppose I take something nice, which can be tiled. What does a random tiling look like? And this was, okay, so I write one name down, Pond, Kenyon, and Prop, but this is a huge, long line of work, which eventually led to this. So what you're seeing over here is what is called an Aztec diamond. If you look at these edges, then there are these dominoes over here. These are perfect dominoes. And you go up in a staircase manner all the way to the top, and then you turn and then you come down again. So that's the region which you're bounding. And what do you see? What are these colors? So these yellow colors are dominoes in this direction. There's a parity associated with it, which I don't want to get into, which is why there's a color, this is colored yellow, and these are also horizontal dominoes, which are colored red. Similarly, you have green over here and blue over here. And now what you should observe from this picture, this is a simulation by a co-author, Martin Tassi, is that you get this very nice shape over here, which looks like a perfect circle. This is what is called an Arctic circle phenomena. This is completely general. You can take any shape, and in general, you'll have this forming, this kind of a boundary in general. And these regions, these boundaries will be given by actual PDEs, which you can write down, provided you gave me the boundary nicely enough. And in fact, you can describe what is roughly going on in this area as well. If you want to know the statistics of these tilings, you can find out a lot about this. And I was enamored by, whether we can extend this to higher dimensions. And, we can't do the exact computations, that is completely out of reach. But we can prove a theorem like this, that we know that there exists some solution like this. There are some asymptotic shapes and for a random object, if you pick a domino tiling randomly. So we have some very rough simulations. And sorry for going a little over time, and so this is, can everyone see a domino tiling here? So this is the three-dimensional analog of an Aztec diamond. This simulation was done by my co-author, Catherine Wolfram. And you can see some sort of pattern emerging over here, where these colors are the same. This yellow matches up. The purple over here is sort of uniform. It's already a question, how do you simulate such a thing? How do you pick a uniform object out of all these exponentially many possibilities? This is already a very difficult question in this particular case. But we are still refining the algorithm, and hopefully we'll have better pictures to show next time I give a colloquium. So let me go back to the slides. Okay, this now works. And right. So that is all I had to say for now. And with that, I end my talk. So these are various people who are associated to whatever I've spoken about. And I thought that I would give them a nice homage.
You're done a tiling of those people, it looks like. So if I get your this work correctly, so you have some let's say you have some tiling, and you want to get suppose from all the configurations of given tilings, you want to pick some random tiling and answer statistical questions, like maybe is there a, I don't know, a cluster of this particular color or whatever, some patterns. Is that correct?
That is right. So okay, so we can't actually find out the statistics, but we know that it follows some differential equation. So we prove existence of such objects. It's a solution to a certain variational problem. That's what we prove. So if I were to go back to this. So the key point here in Koenig and Nientrop's work is that everything was written down explicitly. We can't do that because we don't have the same tools. but we can prove existence that of some asymptotic shape of and the fact that all these, what is happening in this region is also given by a variational form problem. And similarly, like if you take a large enough box in a very big region in R3, then we will be able to sort of tell you roughly what the statistics should look like. So it's more of an existence result in that sense.
Okay, thanks. I mean, I would be interested to know what is that variational thing, but okay, maybe I'll ask you next time.
Okay, so are there other questions or comments?
Shant?
Yes.
So,
Yes,
just observational thing. So I see that the boundaries here seem to not interact much. So is there any like a sandpile type of a reference or these boundary growth models?
So I definitely know that sand piles are related, but I don't know an exact reference or even a precise explanation. I don't know much about sand pile models, frankly. So,
but is there any reason why the boundaries are not interacting?
Yeah, they are frozen. So this is essentially okay. So they need not be frozen. I here what the tile that I have at the top is like this.
Right.
Like,
Mm-hmm.
I could have instead have had a tiling like this.
Correct.
Right?
Mm-hmm.
This is what the top looks like.
Mm-hmm.
But it turns out that if you actually look at it entropically, then this is there are a lot fewer tilings which will follow this rule than compared to this rule. That's more or less the explanation I can give right now. So if you follow this through, what would you get? So you would maybe place a tile over here, and then you would be, so you would, here the advantage of putting things in this way is that you're more or less flat when you come around over here. So what you're trying to do is essentially, as far as possible, given all these boundary constraints, flattening this region as much as you can. Okay, now this sounds a little contradictory given that I said that you want to form the circle in the limit, what you get. But that's essentially, you're trying to do the best because this is trying to pull it in a different way. This is trying to pull it in a different way. And that's very, very vaguely the explanation for this. But
so is so when you are going when you are trying to get to the variational principle, variational formulation rather, is there any like there? Do you like use the connections? Because I mean, this problem is looking very hard to look at. I mean, in general, but if I consider the height growth models or the crystal growth models, they look a little like at least the thermodynamic limit or in any other limit, it seems a little more manageable because there is a martingale you can extract and so on and so forth.
So when you say in a height growth model, do you mean that there is some height associated with these tilings and you can look at them instead of the tilings?
No, there is no tile. So I'm not even thinking of it, I mean, in terms of tiling. So the thing is that we can think of this as like a flat object, and let us make it even in fact of a one-dimensional thing. So what you have is basically things falling, and then all the things falling are basically forming the height. And then you basically compute the.
So for example, like corner growth model, and there's
right, correct, exactly. Yeah.
So there are things associated with that, and they are often useful in this context. Depending on what question you precisely ask. In fact, even in 3 dimensions, there is some analog to this. However, as far as I know, it can't be directly used in this particular problem. There are other contexts in which this can be used. And there is a height function associated with it. It looks like a 3-dimensional object.
Exactly, it does look like, which is why I
The reason is, there's a very good reason for this. Associated with any domino tiling of the 2-dimensional plane, there is a height function. So what you get in the end, when you look at the height functions, is a random surface. Actually, not a random surface, it's a what should I say? So you start with these random surfaces, discrete surfaces, and you scale them away. What you get in the limit is something very, very non-deterministic. It's a solution to a variational problem. So this is exactly what the solution to a variational problem is. In 3 dimensions, it turns out that there is no height function, and this was a major stumbling block for a lot of years. There's hardly any work on 3 dimensions for this. But instead of heights, it turns out that there are vector fields associated with these domino tilings, and so we associate. So it turns out that once you are given a region, and now you scale it again, then the limiting object, now instead of looking like a random surface, will look like a random vector field. And this is what we prove.
I see. Okay.
I'm sorry for being so vague, but I think this would be at least 2 or 3 talks to at least like describe precisely.
Okay, thank you.
So any other questions? So if not, so let's thank today's speaker Nishant for this wonderful talk. So thank you, Nishant.
Thank you for listening.
Yes, I guess we'll meet next week at the same time.